The focus of this video lecture is on electric charge and electric force. We will define what they are, describe how they behave, and look at some practice problems. The electric force is the force between electric charges that are at rest or nearly at rest. For this reason, it is also known as the electrostatic force. It was discovered more than 2,500 years ago by ancient Greeks through the triboelectric effect, which is the process in which materials become electrically charged through friction. For example, if you rub amber, which is fossilized tree resin, with fur, the amber becomes negatively charged while the fur becomes positively charged. This is essentially how static electricity is generated. The ancient Greeks discovered that this amber can attract light objects such as straws. Because of this, the word electron originates from the Greek word for amber. By conducting experiments using triboelectric effect, and also through other experiments, people made three basic observations about the electric charge and electric force. First, electric charge comes in two flavors, positive and negative. Second, two positive charges or two negative charges repel each other. And third, a positive charge and a negative charge attract each other. Back when people were first discovering these basic facts, they did not know what was happening to the materials when they become charged, and we had to wait until the development of the atomic theory of matter to understand what it means for a material to become electrically charged. The atomic theory tells us that all matters are made of atoms, which consist of nucleus made of protons and neutrons, and electrons around the nucleus. These subatomic particles, neutrons, protons, and electrons, have the following electric charges. We will use Q for the electric charge. The electric charge on neutron, or Q sub n, is exactly 0, so it is electrically neutral. Each proton has charge Q sub p, which is equal to positive E, or positive 1.6 times 10 to the negative 19 coulombs. The charge on the electron is exactly the opposite of the charge on the proton, so each electron has charge Q sub e, which is equal to negative E, or negative 1.6 times 10 to negative 19 coulombs. Here, Coulomb is the SI unit for electric charge, and we will use capital C for the unit. A typical object contains many atoms, with each atom possibly having multiple protons and electrons. For this reason, an object is said to be positively charged if the number of protons it has is greater than the number of electrons it has. On the other hand, it is negatively charged if the number of protons is less than the number of electrons. It is neutral if it has equal number of protons and electrons. In most solid objects, electrons are mobile, while protons are relatively immobile. For this reason, objects typically become positively charged by losing electrons, and they typically become negatively charged by gaining electrons. Here's one fundamental fact about the electric charge. Because most objects are made of atoms, electric charge can only come in integer multiple of E. Because of this, E, which is equal to 1.6 times 10 to the negative 19 coulombs, is said to be the fundamental unit of charge, and any charge on an object can be written as E times some integer. There's another fundamental fact about electric charge, and that is the conservation of charge, which says in any closed system, the sum of all the electric charge is the same. Another way to say this is that the electric charge cannot be created or destroyed. Let's consider an example. In nuclear physics, there's a process called neutron decay. In this process, one neutron turns into one proton, one electron, and a subatomic particle called antineutrino. Here are the charges on each of the subatomic particles. The total initial charge is just the charge on the neutron, which is equal to 0. The final total charge is the sum of the charges on the proton, electron, and antineutrino, which add up to 0. Because total charge initial is equal to the total charge final, the electric charge is conserved. In most processes we encounter in everyday life, one subatomic particle does not turn into another, unlike this example. So for those processes, the conservation of charge essentially implies that the total number of protons and the total number of electrons in a closed system don't change. Let's now consider different types of materials. Most materials can be classified into two categories depending on how easily charges can move from one region to another. In conductors, electric charges can move from one region to another. Metals and salt water are some examples of conductors. For example, in metal, electrons in the outer orbits are loosely bound to the atom, and these electrons can move easily from one part of the metal to another. In contrast, in insulators, electric charges cannot move easily from one region to another. Most nonmetals and pure water are some examples of insulators. Here's a schematic diagram of an insulator, and its electrons in the outer orbit are tightly bound to the atoms. There are also semiconductors, which have properties between conductors and insulators. Let's consider an example. Two identical metal blocks A and B are initially separated. Block A has -4 millicoulombs of charge, and block B is uncharged. What will happen if the blocks are allowed to move freely? Let's think about this step by step. First, the excess negative charge on block A repels electrons in block B, pushing them to the right side of block B. Because there are more electrons on the right side of the block, this induces a negative charge on the right side of the block B, leaving a net positive charge on the left side of the block. Because the positively charged region of block B is closer to block A, which is negatively charged, the attractive force between the two blocks is stronger than the repulsive force. And because of Newton's third law, the blocks exert attractive forces on each other and bring them close until they touch. There's now a conducting path for the electrons between the two blocks. Since the blocks are identical, the total excess charge of -4 millicoulombs distributes equally, so each block ends up with -2 millicoulombs. Now that both blocks are negatively charged, they will move apart due to the repulsive electrostatic force. Let's also consider what will happen if block B is an insulator instead of a conductor. This time, electrons on block B cannot move freely. However, they are still repelled by the negative charge on block A and can shift slightly to the right within the atoms and molecules. This is known as polarization. This causes the right side of block B to be negatively charged and the left side to be positively charged, and the blocks attract each other. Because block B is an insulator, after they touch, there's no charge transfer between the blocks. Earlier, we discussed how charged amber can attract small objects like straws. The polarization of charge is what allows the amber to attract straws even though they are insulators. Let's try to be more quantitative. Coulomb's law describes the force between two point-like charged particles. Suppose we have two particles with charges Q1 and Q2, and they are separated by distance r. Then the magnitude of the force between them is given by this formula. F is equal to K times the absolute value of Q1 times Q2 divided by r squared. Here, Q1 and Q2 are charges in coulombs, r is the distance in meters, and K is a constant and is equal to 8.99 times 10 to the 9th Newton meters over Coulomb squared. Sometimes we prefer to express the force between the point charges in terms of a different constant, epsilon naught, which is equal to 8.85 times 10 to the negative 12 Coulomb squared over Newton meter squared. And this is known as the permittivity constant. This equation is what's known as Coulomb's law. The equation only tells us the magnitude of the force. For the direction, we just need to remember that two positive charges or two negative charges exert repulsive force, while one positive and one negative exert attractive force. We will now work on two practice problems. Suppose 2-point charges Q1 with negative 2 microcoulombs and Q2 with positive 5 microcoulombs are separated by 60 centimeters. We want to find the magnitude and the direction of the electric force on Q1 exerted by Q2. Here's Q1 and here's Q2. And they are separated by 60 centimeters. Let's think about the direction first. Because their charges have opposite signs, the force must be attractive, and the force on Q1 points toward Q2. For the magnitude, we use Coulomb's law. Let's plug in the values. Because of the absolute sign, we get rid of the minus sign for Q1, remembering that micro is 10 to the power of negative 6, we have 2 times 10 to the minus 6 coulombs times 5 times 10 to the minus 6 coulombs, divided by 60 centimeters squared, or 0.6 meters squared. Let's check the units. The 2 coulombs in the numerator cancel Coulomb square in the constant K, and the meter square in the constant cancels m square in the denominator. And we are just left with newtons, which is the correct unit for the force. We can now plug the values into a calculator and find that the force on Q1 is equal to 0.25 newtons in magnitude. And the direction again is toward Q2. Let's now consider a slightly more challenging practice problem. Suppose 2-point charges Q1 with negative 2 microcoulombs and Q2 with positive 2 microcoulombs are located at xy coordinates of negative 0.5 meters and 0, and positive 0.5 and 0, respectively. We want to find the net force on the third particle Q3 with positive 5 microcoulombs located at xy coordinates of 0, 1.2 meters. Here's our strategy. Because both Q1 and Q2 exert forces on Q3, we need to use Coulomb's law to find the force from Q1 and Q2 separately. Then we find the net force by calculating the vector sum of the forces from Q1 and Q2. Here's what the setup looks like. Here are the x and y axes. Here is Q1, and it is at 0.5 meters to the left of the origin. Here is Q2, which is at 0.5 meters to the right of the origin. Q3 is along the y-axis, and it is at 1.2 meters above the origin. We want to find the net force on Q3. We can write the net force as F1 vector plus F2 vector, where F1 is the force exerted on Q3 by Q1, and F2 is the force exerted on Q3 by Q2. To find F1, we can focus our attention on these two charges circled in red, while ignoring the presence of Q2. Likewise, to find F2, we can focus our attention on the two charges circled in blue, while ignoring the presence of Q1. To find F1, we need to know the distance between Q1 and Q3, which I call R. Because of the symmetry of the system, this r is also the distance between Q2 and Q3. To find the value, we can use the Pythagorean theorem, so r is equal to the square root of 0.5 meters squared plus 1.2 meters squared, which is equal to 1.3 meters. Let's find the magnitude F1 using Coulomb's law. Like before, we need to make sure that the charges are in coulombs and the distance is in meters. We can also verify that the units work out, and plugging the values into a calculator, we find that F1 is 0.053 newtons. We can repeat the same steps for F2, but since the charge on Q1 and Q2 are equal in magnitude, and they are the same distance away from Q3, F1 and F2 must be equal in magnitude. So F2 is also equal to 0.053 newtons. Let's now think about the directions of F1 and F2. Q1 and Q3 have opposite signs, so the force between them is attractive. So F1 must point toward Q1. On the other hand, Q2 and Q3 have the same sign of charge, making the force between them repulsive, so F2 points away from Q2. To find the net force, we need to add them as vectors. From the symmetry of the system, we can tell that F1 and F2 have the same x components, but their y components are opposite of each other. So when we add F1 and F2 as vectors, we find that the net force has no y component and points to the left. If you don't see why the y components of F1 and F2 add up to 0 at this point, that's fine. You can calculate the y components using a method I describe next and convince yourself that they do indeed add up to 0. But if you see the symmetry, then it will let you skip unnecessary steps and allows you to find the answer more quickly. Let's make a right triangle using F1 as its hypotenuse. Here's the right angle, and let's call this angle alpha. This triangle and the triangle in green are similar triangles, which makes this angle also alpha. This will become important a bit later. The x component of F1 is equal to the magnitude of F1 times cosine of alpha. This comes from SOHCAHTOA. We need to put a minus sign because it points in the negative x direction. This is equal to negative 0.053 newtons times cosine of alpha. Let's look at the green triangle again. The cosine of alpha is equal to adjacent over hypotenuse, so we can write this as 0.5 meters divided by 1.3 meters. Using a calculator, this is equal to negative 0.0205 newtons. And because of the symmetry, this is also equal to the x component of F2. We can now find the net force, which is equal to F1 plus F2, or negative 0.0205 newtons times x hat plus negative 0.0205 newtons times x hat, or negative 0.041 newtons x hat. Here, x hat is a unit vector pointing in the x direction. The approach we just used is known as the superposition principle, which says To find the net force on point charge big Q due to endpoint charges, we use Coulomb's law to find the force on big Q from each of endpoint charges, then find the net force by calculating the vector sum of end forces. Mathematically, this principle can be expressed this way, where the Greek character sigma indicates sum over all endpoint charges, and F sub I is the force on big Q from the ith charge. To summarize this video, we saw that electric charges come in two flavors, positive and negative, and the electric force between like charges, such as two positives or two negatives, is repulsive, while the electric force between opposite charges is attractive. Broadly speaking, there are two types of materials. In conductors, charged particles can move freely, while in insulators, they cannot move freely. The conservation of charge states that charges cannot be created or destroyed. And lastly, we saw that Coulomb's law can be used to find the electric force between two point-like charges. And it is given by this expression, where epsilon naught is a constant known as the permittivity constant. If there are more than two particles, then the net force on the charge big Q is the vector sum of the forces exerted on big Q by all other charges.